Welcome to When It's Not a Network Problem, identifying higher layer issues in packet data. My name is Wes Morgan. I'm a senior software engineer with HCL Software. I'm based in the state of Kentucky in the US. I'm not going to read all of this to you. I've been around for a while. I came into network engineering early on when we were running thick wire Ethernet through the College of Engineering at the University of Kentucky. Basically, I go back to the days of punch cards and paper tape. So I've seen quite a bit over the years. My first experience with Wireshark, or what we now know as Wireshark, was actually Ethereal release 0.4, which I built under Red Hat Linux 5.2 on an IBM ThinkPad 560Z, which takes us back to about 1999. So I've been using this for quite a while. Let's jump right in. Why are we here? Well, we're here because whenever application troubleshooting starts, there's almost always someone who says, well, it could be a network problem. Well, in my experience, that's only correct maybe 1 out of every 8 or 10 times over all the years that these things have landed on my desk. That's about how often I do find an issue at the network layer. However, I've learned that we can often see some important clues to operating system issues, application layer issues in packet data. So what we're going to do today is talk through some case studies to give you an idea of some things that you may see in your packet data. It's always important before you start this type of analysis to understand the environment. A few critical points. Are we talking about physical hardware or a virtual machine? Is storage local or remote? We need to know what intermediate devices are present, firewalls, proxies. You may see things like ICAP, content management servers, that sort of thing. And I want to make it clear, we only go to this level of analysis after we've ruled out network layer concerns. So you're looking at it through the lens of a network engineer, and you've said, this capture is basically clean, retransmissions are non-existent or well within acceptable limits. We don't identify any examples of congestion or packet loss or unexplained delays. You know, this is you do not start looking for this stuff first. This is after you've ruled out network layer concerns. You're going to need some understanding of the application in question and the protocols it uses. Some of these will be illustrated in the case studies. And finally, you have to understand the problem you're looking for. Is it constant? Is it intermittent? Can it be easily reproduced? These are the kind of things you have to have done before you move up to this layer of analysis. So let's just get started. Sometimes all you need is a basic timing analysis. And this is where Wireshark's computed TCP.time_delta attribute is most useful. You may consider adding it as a column just to make it more visible. Even when the traffic is encrypted, you can identify request response patterns. You can correlate those with application or operating system logs. And you do need to, again, understand the nature of the request in question because it may lead you elsewhere for troubleshooting. Let's take a look at a straightforward example. Now, if we look at the time delta in the third column, this is just a simple TLS transaction. And we look at the handshake, we look at acknowledgements within the conversation. They suggest a network latency of about 43 milliseconds, right? You can see that between the SYN and the SYN-ACK, about 43 milliseconds. However, once we issued a client hello, and it was acknowledged within, in this case, 47 milliseconds, but then it took over a full second for the server to respond with its server hello to continue the TLS handshake. Well, 1,115 milliseconds just to process a client hello. We need to check that out a little deeper. So instead of looking at a single conversation, I'm going to pull out every instance of this server responding with a server hello. And we see in the delta column, it is consistently taking 1,000 milliseconds or more, a full second, just to process a client hello and come back with a server hello. That's something they're going to want to investigate, right? That's adding a full second of overhead to every single conversation on the box. This is just the simplest example, but this is one where you will often get your first clues or your most obvious clues. Let's take a look at another example. Now, in this case, you look at the time column, and we're only talking about a 46-second conversation. And you can see in the info column, it is just an HTTP GET. And we're getting continuation traffic. So it's having to either compute or retrieve data piece by piece to complete its response. But again, look at the deltas, look at the dead air. Okay, so here is 7 seconds that we're waiting on that remote server to give us some data. Here's 13 seconds. Here's another 7-second wait. And notice when we receive data, the responses are fairly quick. And finally, another 8-second piece of dead air, all in the context of a single HTTP response. So I said this was a 46-second conversation and a single HTTP GET request. 35 seconds were dead air. That would be a case where I go back to the applications team and say, is this expected behavior? Right? We're adding 35 seconds of overhead to this conversation, to this transaction. Is that necessary? Is there anything we can do to optimize that at the application layer? Because again, notice this is not a network layer issue. There are no retransmissions. There are no indications of congestion or loss. This is straight up dead air. The application is not talking to us. So this is an example where you would definitely go back to the applications folks and say, do you realize you're making clients wait for 35 seconds in this case, especially if you see this reproduced. In this case, I actually saw this behavior every time we went to this particular URL. So when you see it reproduced multiple times, that's a huge clue that there's something going on at the application layer. Another one we see not quite as often is the server response delayed for such a long time that the client actually gives up. And what you wind up with is traffic after the client has sent a FIN. You'll often see this across multiple conversations, and you may see it intermittently depending on the transaction load of the server in question. And this is a case where, again, understanding the nature of the request can be your biggest clue. And when you're examining this, you want to understand what external dependencies there may be, because that may point you in a different direction to resolve the issue. And we have one example of this, and both the sequence and the timing of this example are significant. We notice in the time column, the TCP handshake and the initial client request are all processed as expected. They're all processed in a reasonable amount of time. And then we have 60 seconds of nothing, 60 seconds of dead air. And here's a general tip for network analysis. Never trust round numbers. If you see something that is consistently occurring after 30 seconds, plus or minus a few milliseconds, 60 seconds, 120 seconds, that is almost always indicative of a timeout, whether it's on the client, the server, or an intermediate device. But that's almost always your clue that something has run up against a limit, a configured limit. And that's what happens here. The client times out on its request and it sends a FIN. And we notice that FIN is acknowledged immediately. So we know that the TCP/IP stack is responsive. Well, then 2 seconds go by, in this case 2.5, and the server finally comes back with a 200 OK response. Well, but the client's already timed out. So it's going to just ignore that and throw a TCP reset. Now, remember I said understand the application and the protocols it's using. Let's take a look at that specific request. What was the client trying to do? RTC auth /verify.jsp. Well, it's a reasonable assumption that a URL including the phrase auth is authentication. And that's what it is in this case. Well, authentication normally depends on a directory of some sort. And in this case, the root cause of this problem was found to be an extremely slow response time for the back-end LDAP server that was being used for authentication. So this was another example where it might get presented to you in one context, but the data you find in your packet captures points you in a different direction to resolve the issue. The next one is what I call a request backlog. And again, let's reemphasize, no TCP/IP error conditions, no packet loss or congestion evidence, but we've got dead air again in the responses from a service. It may or may not accept additional requests. And then all of a sudden, you get a flood of responses. Now, it's important to note, you may be alerted to this by using Wireshark service response time dialogs, which are present for many popular protocols. For instance, you may look at the service response time for LDAP, and it may say, oh, your average was 2 milliseconds, but your maximum was 10 seconds. Well, if you see that in the service response time dialog, you're going to want to go look and examine, what transactions took 10 seconds to complete when it's a simple LDAP query. And as a matter of fact, that happens to be the example we have. And looking at this top screenshot, you'll see search request, search result, search request, search result, search result, search request. And you can see that we're roughly in step. I make request number 365, then I get my results for 361 and 363 and 364. But then all of a sudden, I stop getting responses. In the meantime, I'm still making request after request. Again, no TCP/IP error conditions. We went 7 seconds without a server response. And in that period of time, as you can see in the bottom screenshot, we got up to 110 requests or more that are now backlogged, right? It accepted up to our 473rd search request. And then it came back with the result for search 366. Now, here's where that snowballs. Because we had this 7 to 8 seconds without a server response, once we start getting them, we're so far behind that we're going to add additional time to process each search result. So all these transactions that are waiting on search results are going to be delayed by 7 to 10 to 11 seconds, depending on how far in the backlog they were. This is something you often see when LDAP is used for authentication. You'll also see it in applications that manage contacts by consulting an LDAP directory, basically anything that has a high volume of LDAP searches. Moving on to HTTP, and with the ever-growing number of web-based applications, this one comes up more and more frequently. And Wireshark's computed HTTP.time statistic is your friend. This is what's going to be your biggest help. Now, it's flexible. There are 2 different measurements of HTTP response, and it depends on your Wireshark configuration. You'll have all the HTTP reassembly preferences enabled, but then you go to the TCP preferences. And if you do not allow the subdissector to reassemble TCP streams, HTTP time will be the elapsed time between the request and the first packet of the response. In other words, the response code, 200 OK, 404 not found, etc. If you do have TCP reassembly turned on, then HTTP time will be the time between the request and the last packet of the response. So from our perspective of looking for application layer issues, when would we change this one way or the other? Well, in most cases, you're going to look for that first response packet, and that's the time you're interested in. However, I have seen issues where, with remote storage, a poorly configured SAN or an overloaded SAN, for instance, the actual delay came between the server's initial response code, 200 OK, and the beginning of data flow. So there will be times you look at each of these. values for HTTP time. You'll just flip between the two configurations. You might even do that in a profile if you wanted to. We're going to use the first example. We are not reassembling TCP streams. So HTTP.time is going to be the time between the request and the first packet of the response. This is the profile I use for HTTP troubleshooting. You can see I have time delta as a column. I also use HTTP request, HTTP response, HTTP time, return code, and payload size. So I can look at any one of these and say, this is a response, and it is a response to the request I made in packet 1283. Here is my request, a new request, and its response is in packet 1373. Might also know, since we're talking about a profile, I've created buttons specifically for HTTP, not just to isolate HTTP traffic, but also by return codes, by transactions with a delta larger than 2 seconds, not an HTTP time greater than, but a TCP delta greater than. Show me all the gets, show me all the posts. Well, we see 3 responses in this time, in this frame, and 2 of them are fine, right? Ballpark 55 milliseconds, one way or the other. But here's one that took almost 2.5 seconds, full seconds, before it even came back and said, okay, much less gave me the data. That's the sort of thing where you would look through the rest of your data. Is there a pattern to be found? Well, and in this case, there was. We only saw these delays when we were doing gets against a particular type of data. In this case, pictures. So now, instead of the web page is slow to load or HTTP is slow, we've refined the problem statement down to the server is experiencing delays retrieving these particular pieces of data. And in this case, ultimately, we found the root cause was poor performance on the server that was hosting those images. Because behind the scenes, the HTTP server was having to go to a remote storage service to get those pictures. And that was where the delay was being introduced. So once again, there are no TCP/IP error conditions here, but we found major clues that led to huge performance improvements at the application layer. And that's the kind of thing we want to do. I remember when I first saw this case study, and this was the first time that I had to go this deep into the operating system side of TCP/IP networking. The issue displays as the TCP/IP stack completes the handshake, and then all of a sudden you see a reset. Now, we've all seen cases where you can't complete the TCP handshake, right? You send a SYN packet and you never get a SYN-ACK, or you get a reset immediately when you just try to start the handshake. This one's different. The handshake completes, but then we get a reset. And I found this very confusing until I realized the initial handshake is controlled by the TCP stack, not by the application, right? The application establishes itself as a listener, but it does not process the initial handshake. What happens is, As the stack completes each initial handshake, that conversation is moved over to what's called a listener backlog queue. And each listening application has its own queue. Well, there are three things that can happen here. The application can come down, say, oh, okay, that conversation is waiting for me, and it initiates the application layer dialog. That's the normal occurrence. Well, if for some reason the application does not pick up the conversation from the backlog queue within a reasonable amount of time, the TCP stack will kill it with a reset. And the stack will do the same thing if the backlog queue is full and additional conversation attempts come in, new clients come in, they're rejected after the handshake with a reset. If you are familiar with IBM's AIX operating system, you may have noticed that in its netstat output, it makes references to embryonic conversations. That statistic covers everything until the application picks the new conversation up from the listener backlog queue. So the resolution here is to increase the backlog queue size at the OS or the application layer. There are some applications that do manage their own backlog queue. You can configure it from the application. HCL Domino is one such application. You don't want to go overboard there. You know, you want to take the current value, you might add 10%, but you cannot just triple that value or even double it, because this problem only happens when the server's under stress, right? Or the application is under stress. So increasing the backlog queue, yes, it can resolve the issue as long as the load stays constant and you enlarge it enough to accommodate the load. Otherwise, you're just going to run into the problem again. And then you're going to have another round of troubleshooting to figure out why the application isn't playing well with its backlog queue. Moving on. You have to check every layer of troubleshooting. You may have a problem brought to your attention, but it's brought to you with an incomplete or erroneous definition. So let's take a look at this example. This problem came to our attention as voice over IP problem, calls are failing. And we asked a few questions and they said all calls involving this server are failing. Well, the folks who did their initial troubleshooting focused on the SIP stack, right? Because that's where the calls are negotiated. So if the call is failing, well, then SIP is failing, was their thinking. The key factor that they didn't consider, it wasn't just SIP. It was SIP-S, secure SIP, SIP over TLS in use. Well, now we're going to need to check every layer. Let's examine what's going on with TLS. And that's when we saw this pattern in the data. You see the TCP handshake, it's just fine. The client gives its client hello. We're expecting to see a server hello in response. Instead, we get an alert and a close notify. Basically, at the TLS layer, the server's saying, shut up and go away. Well, Obviously, that is not what we should see. So further investigation and a review of the server's configuration found errors in the server TLS configuration, and that was the root cause of the issue. So this is a really good example of the fact that you cannot just assume your problem lies at the application layer. And I'll also say that from a networker's perspective, we look at this and, we don't see TCP/IP errors. There, again, the things people normally use to blame the network. There are no retransmissions, there's no packet loss, everything checks out, but we go up one layer to TLS, and then we find the issue. This happens very frequently. Another one that people have experienced, and some of you may have experienced it, is, you're with your laptop and you roam to a new access point that gives you a different IP address. All of a sudden, all your applications are dying, right? Well, that's actually happening up at the DHCP layer. That's the root cause, is that you pulled a new IP address that left all your running applications in limbo. So again, this is the warning to check every layer. We're going to take some time here because what we're going to go through right now, in my experience, is the most common indicator of a problem at the OS or application layer. Now, for those of you who may be unfamiliar with Tcp Zero Window, that condition simply means that the TCP receive buffer for the endpoint has filled, right? Because you know that during a TCP conversation, both sides constantly tell each other, here's how much data you can send me. Here's my window. I'm ready for up to this many bytes of data, whether the window is scaled or not. That's really all it means, is here's how much you can put on the wire without waiting for me to acknowledge it. I've got room for this much data. Well, that also means that if that window fills up, if the window goes down to 0, no further data can be sent by the other endpoint until space is available in the window. So the critical question we always have to ask is, why has the receive buffer filled? Now, the short answer to that question is, well, the application isn't retrieving data from the TCP receive buffer in a timely fashion. Right, that's the obvious part. You're going to need to talk to the OS and application folks to determine why the receive buffer is filling up, why the application isn't coming down to retrieve data in a timely fashion. Now, I'll give you a word of warning. You will sometimes see very short-lived instances of TCP Zero Windows. And when I say short-lived, I'm talking about 10 to 20 milliseconds at the most. Those may just be a hiccup. Check them anyway. I always look for TCP Zero Windows whenever an application performance issue comes my way attached to some packet data. I mean, if it's a here and there thing and it's only, 5, 10, 20 milliseconds in duration, that could be a sign that the server is beginning to struggle, but those short-lived instances are unlikely to impact either application performance or client experience to a significant degree. Where you definitely want to be concerned is if you see either lengthy instances, long-lived instances, multiple long-lived instances, or simultaneous instances across multiple conversations. If you see any of those in your data, that's almost always an indication that there's a resource contention issue going on at a higher layer. It could be a semaphore block. It could be a threading issue. You may see issues where in a virtual environment, the whole VM is waiting for CPU and it can't process the data until it gets CPU cycles to do it. So this indicator can point you to any number of directions. So let's look at a few examples. Here's a trivial example of a TCP Zero Window. I will tell you that this is one that only happened twice in the entire packet capture. And you can see it resolved itself within a millisecond, right? So we received some data, we responded with a zero window, but then within a millisecond, we started recovering. The window went from 0 to 3K, 3,760 bytes. And within that same millisecond, it went all the way up to 64K. So we have a very short duration, only 1 millisecond, and we have a quick and almost full recovery because the window went from 0 to 64K very quickly. This is definitely a hiccup. Okay, again, unless these little short duration zero windows happen frequently, they're usually not too much of a concern. It's kind of the cost of doing business. Well, let's look at a little bit bigger problem. Now, in this case, we have a fairly long duration, 4 seconds, in fact. And we also have a slow recovery. Notice that as this zero window was resolved, the window was only restored to 5K, from 0 to 5K, and stayed there. Last piece to notice, the other side was waiting to send data. You may have noticed in our previous example, we did not see zero window probes from the other endpoint. Well, that's because at that time, the other endpoint didn't have any data to transmit. Well, in this case, the other endpoint does have data and it wants to transmit. So it's going to send a probe to see if there's still a zero window. And it's acknowledged with another zero window condition raised. And that goes on for 4 seconds. Notice the deltas between these attempts, right? 600 milliseconds, 1.2 milliseconds, 2.6 milliseconds. Zero window probes multiply the round trip time, just as do retransmissions. So in this case, we've actually added 4 seconds of nothing to this transaction. This is the sort of thing that you do want to bring to the attention of the applications and operating system people. Because this is definitely, no application should be waiting 4 seconds to empty out its TCP receive buffers. Our final example here is an excessive system-wide stress indicator. And I say that because first, it's a very long time span. This is from 4:14 a.m. through 4:21 a.m. So this is 7 minutes almost. You see that multiple protocols are affected, right? We have TCP Zero Window responses from the HTTP server, from a client process talking to a remote server, to a server process talking to other clients. So we have multiple protocols affected, multiple conversations affected at the same time. So remember I said we were usually looking at resource contention or threading issues when we saw a large number of TCP Zero windows. Well, this is as clear an indicator as you're going to get, because we have multiple conversations affected at the same time, and these are being driven by multiple threads at the application layer, and they're all happening within a long span of time. So this is a very clear indicator that this system is under a general stress condition. And I will tell you, in this case, this happened to be a virtual machine that was starved for CPU because the VMware host had too many virtual machines running concurrently. And the place where you want to check for that in the VMware world is a statistic called %CPU ready. And that is, how often did this virtual machine have work to do, but had to wait for CPU cycles to do it? And that is an automatically generated statistic. And VMware's own guidance says if that number is above 5%, 4 to 5%, then your VMware host is overly burdened. The word is overcommitted, right? You've committed too many VMs to run concurrently. This is an increasingly common issue we find among the customers with whom I work. So this is probably the most common example of system stress that you'll see in packet data. Now, that's all we have for the discussion. I'd certainly like to hear any questions you might have, so I'm going to go to the chat. All right, I'm just going to go through the questions in order. If we're capturing on the client side, could dead air be the result of traffic shaping along the path? That is possible, and that is one reason why we started the discussion with understand the environment, right? That's part of your initial questions as you're troubleshooting. You know, is packet shaping taking place? I will say that the comparison of timing within the conversation can be a big clue, because if you're tooling right along with a very short response time and everything looks clean, and then all of a sudden you run into a brick wall and you have dead air for 7 seconds or 10 seconds, that's probably not shaping. Because even when shaping kicks in, most algorithms do it as a trickle. You won't see a zero, you know, a 60 mile an hour to zero, and you won't see a 0 to 60 miles an hour. If traffic shaping kicks in response to congestion, you'll see a gradual change. You won't see this sudden dead air. in most cases. There are cases where printers use TCP Zero Window to earn time for ink heating. Wow, Marius, that's interesting. I did not know that. Makes sense. I'm going to have to look at my printer traffic the next time I change the ink. Thank you very much for pointing that out. I've learned something this morning. Marcus asks, how can you determine which application at a higher level is raising the TCP Zero Window conditions? Again, this is a situation where knowing your application can help. The other thing you can do is on the server side, you can use netstat to show the processes associated with each listener. And I believe that is a -B. So let me jump onto a -B, and you will need administrator privileges to do this. So again, just be aware of that. But yeah, you can use netstat -B, and it will tell you what executable owns that conversation or that listener. So you can at least get it down to a particular application, if not a particular instance of that application. And that's netstat -B. Dennis gives us another comment regarding Zero Windows and printers. Thank you very much. Again, I was not aware of that. What would you consider a reasonable ratio of retransmissions? I'll be very honest with you. This is a battle that I fight quite often. Personally, from my reading of the TCP/IP specifications, I believe that the TCP algorithms for duplicate acts, for retransmissions, for fast retransmissions, anticipate a packet loss of 3 to 5% at the most. So I do not call out retransmissions as a problem in and of themselves unless they're at or above 5% of the traffic in question. And it's very important when you look at a packet capture to understand that if you ask Wireshark, hey, show me tcp.analysis.retransmission, it's going to show you all of them across all conversations, which may skew the numbers, your perception, I should say, of the application you're examining. So for instance, if I wanted to consider a particular web server, I'd use a display filter, something like IP address equals X and port equals 80 or port equals 443 and tcp.analysis.retransmission to make sure that I'm only counting retransmissions for the server I'm interested in. Now, I started off this answer by saying I have this argument a lot. I have worked with customers who have said, I come back to them and I say, okay, I'm looking at a capture between a single client and a single server, and the retransmission rate is 42%. That's excessive. 42% of the packets are getting dropped or delayed to the point that the client has to retransmit them. That's not good. And they've come back to me and said, no, that's what we expect on the because of the WAN that we have. So they just think a 42% retransmission rate is the cost of doing business. Obviously, I disagree. So that is something you're going to have to determine in the context of the environment, right? Is it links within the same data center? Is it conversations that are going out a low bandwidth DSL line? Is it a client in New York talking to a server in Delhi? Because that's obviously going to be slower and more prone to packet loss and retransmissions. I think you're going to have to find your own answer to that, or at least be prepared to consider a different definition of reasonable for the environment in question. Nicholas telling us for process names associated with network conversations and listeners in Linux, you want to use netstat-p. Thank you for that tip. I'm going to move over to the Q&A. All right, and the only open question I see is the one we've already answered about a reasonable ratio of retransmissions. So we have a few minutes left. I want to thank you for your attendance. If you're interested in such things, I am on Twitter at Wes Morgan 1. Advance warning, if you follow me on Twitter, you'll get a little bit of everything from football. I'm a Barcelona fan. To music, to networking, to politics. It's a little bit of everything. So you're welcome to follow if you like. I'd enjoy hearing from you. If there are no further questions, Angela, I'll turn it back over to you.
Thanks. Great session, Wes. Yeah, I think we can close things out. And if anybody has any more questions for you, they can reach out on Discord. There's the Zoom 2 voice channel as well.
Yes, thank you. I forgot to mention that. I will be on the Discord for about half an hour to an hour.
Great. Well, thank you very much, Wes. And don't forget to fill out the feedback survey as well. I will post a link to that right now.
All right. Again, thank you for attending, and I hope you enjoy the rest of Shark Fest.